Hi guys, this is another video about how to use projections to find distances between various objects in three-dimensional space. In this problem, we're going to find the distance from the point 0, 1, 1 to the plane 2x plus 3y plus 4z equals 15. The very first thing we want to do is draw a rudimentary diagram of our situation. We want a plane and then we want a point sort of hovering in space away from the plane. I don't care about where the point is in relation to the plane. This is just to help us understand exactly what's going on. Now, just like in the other video, it's frequently pretty difficult to figure out where to start thinking about these questions. So it's nice to break down our plane into the two components that we need to determine a plane. Remember that we need to know a point in the plane and a normal vector. Well, there are an infinite number of points in the plane that we could choose, but let's start with the normal vector. Looking at this equation, we know our normal vector is going to be 2, 3, 4. Let's draw that in. And yes, there are an infinite number of points in the plane, but let's just pick an easy one. As I'm looking at the coefficients on x, y, and z, I note that 3 is the only one that's actually a factor of 15. So I zero out the other two and I find that the point 0, 5, 0 lies in this plane. I'm going to draw it in any arbitrary place. So we have a couple of pieces of information. We have a point that's in the plane, we have a normal vector, we also have this point that's floating off in space away from the plane, and we want to find the distance from that point to the plane. So let's draw in what that distance is in our picture. In Euclidean space, when we want to find the distance between two things, we're talking about perpendicular distance. So that means that this red dotted line here, line segment I should really say, is the length of that is the distance that we care about. And so right off the bat, especially if you've just taken a look at the other video on projections, we notice that the length of our distance right here is parallel to our normal vector right there. Interesting. Let's take a look and see what would happen if we connected the point in the plane out to the point in space. There it is. Note that I've labeled and named these points so that we can talk about them in an easier way. Q is the point that's in the plane, P is the point that's out in space, QP is the vector that goes from the point in the plane to the point out in space. And especially if projections are fresh in your mind, you can immediately see that the length here of our red dotted line is in fact the component of QP in the direction of our normal vector, which I'm going to call n. Again, if this is a little hazy, do make sure to review how projections work, what it means to talk about the component of one vector in the direction of the other, since it's really important to understand those things in order to view this problem correctly. So this red dotted line is the component of QP, our yellow vector here, in the direction of n. It is the part of QP that is pointing in the same direction as the normal vector. All right, well, we know how to calculate that, and that is by taking the dot product of QP and the normal vector and dividing by, the length of the normal in the bottom here. Now you may be wondering, why did I put absolute value signs around it? Well, the component of QP in the direction of n can be positive or negative depending on whether QP is pointing in the same direction as n or pointing in the opposite direction as n. And note that our convenient way of drawing this diagram is not necessarily how this is really laid out. So you may actually have a normal vector that's pointing in this direction, down here, so that the component of QP along that normal, if we were pointing in that direction, would actually be negative. But we don't care about positive or negative because all we care about is actually just the absolute value of that. What we care about is the magnitude. We don't care about the sign in this particular case. The sign is going to tell us whether QP and n are pointing in the same direction or the opposite direction, and the magnitude of this is actually going to tell us the distance that we want here. So let's get computing. If we have the dot product in the numerator and the magnitude of the normal vector in the denominator, our final answer is going to be 8 over root 29. And in fact, that is the length of our red dotted line there. Any questions at all, please don't hesitate to ask. And if you're confused about projections, please make sure to check out the other vector projection video. I think it can clear up a lot of misconceptions.